Hi everyone. Previously on our discussions on Schmidt triggers, we looked at circuits to realize Schmidt triggers with symmetric and asymmetric threshold voltages. Now in this lecture, I'll talk about some other ways of realizing Schmidt triggers with asymmetric threshold voltages that has not been discussed so far. So the first approach, when we talked about Schmidt triggers with asymmetric threshold voltages, we talked about two popular approaches. One approach is by choosing two different feedback factors, beta 1 and beta 2. That is the first approach. The second approach, we said that we'll choose the same feedback factor for the high to low and low to high threshold voltages, but we'll add a fixed offset voltage. By adding the fixed offset voltage, you can then shift the transfer characteristics to the left or to the right, which will result in asymmetric threshold voltages. Now, can you think of a third approach which doesn't involve both? I mean, we will have the same feedback factor and we will not add any offset voltage. Can you still get a asymmetric threshold voltages? The answer to that is yes. How do we do that? The only other parameter that we haven't touched, we have assumed to be constant so far. Only other design variable is the supply voltage, right? We assumed VSAT to be constant so far. But what if you can change that? If you can change that, then the threshold voltages will no longer be plus minus beta VSAT. It will be beta VSAT 1 and beta VSAT 2. In case of a non-inverting Schmidt trigger, how do you analyze non-inverting Schmidt trigger? Assume that your input voltage is a huge negative voltage first. Okay, if it's a huge negative voltage, that's negative voltage is going to the positive non-inverting terminal, so output voltage will be negative. So here it's a dual supply op amp, but the positive dual supply circuit, the positive supply is at plus VSAT 1, the negative supply is at minus VSAT 2. So if this is at minus VSAT 2, you are at this point. Okay, so now you can derive an equation and find out what is the threshold voltage. The low to high threshold voltage will be beta times minus of beta times the negative supply, which will be your V low to high. You can easily show this. It will be beta times VSAT 2, right? I'm not deriving the equations. I'll leave it as an exercise to you. You can just write the KCL at this node and use this condition. When does VD becomes greater than 0? Okay, differential voltage at this node will be simply the factor. You can find out use principle of superposition and find that node voltage. Okay, and you can show that the low to high threshold voltage will occur at plus beta times VSAT 2. Similarly, you can show the high to low threshold voltage will occur at minus beta times VSAT 1. So now if you see here, we have two equations because VLH and VHL are given to you, right? You're given the threshold voltages are given to you. Now you are supposed to design it for design the circuit so that the Schmidt trigger has these two desired threshold voltages. So you have two equations and two unknowns. The thing is that these two equations are not linear. Okay, and what it turns out that this circuit will not have a unique solution, meaning there will not be a unique value of VSAT 1 and VSAT 2 which will give you the desired low to high and high to low threshold voltages, right? So here if you see these two equations, you have three unknowns. You have beta, VSAT 1 and VSAT 2. So now, and you have only two equations. So therefore you will not have a unique solution, but we can impose some conditions. You can impose some conditions that VSAT 1 and VSAT 2 should be very close to plus minus VSAT. You can't have them far away from plus minus VSAT. So we can impose a third condition like that, but leaving that aside, I'm just showing you guys, if there is another approach to build it, this is the way to go for it. Let's say you don't have a reference voltage available. Okay, you don't want to add an additional offset voltage, and you immediately don't have diodes with you. Okay, let's say you don't have access to diodes in the lab, and quickly you want to slightly add some asymmetry into your Schmidt trigger characteristics. You can do it by this way. Just slightly modify the supply voltage, the positive and the negative supply voltages, and naturally you will end up getting asymmetric threshold voltages. So one thing you can see, if you just divide these two equations, VHL by VLH, and take mod of that, you get a very interesting result. Meaning, you know VHL and VLH values, then the ratio of the supply voltages, VSAT1 and VSAT2, should be equal to the ratio of the threshold voltages, okay, the absolute value. So absolute value of those VSAT1 and VSAT2 is determined by beta, okay. So you're using those, you can actually come up with a range of solutions which will satisfy this. So the important point here is, I'm just trying to show you guys that this is the way. Sometimes when circuit techniques like this will be very helpful when you are debugging analog circuits. Sometimes, let's say you built let's say you built an integrated circuit, and you don't have access to go and tweak the resistor values, or you don't have access to go and tweak the reference voltage, the offset voltage, but still you want to somehow get a asymmetric threshold voltage out of it. One trick that I'm telling you guys that you can do is by just making the supply voltage itself asymmetric. Okay, you apply a slightly higher or lower negative supply voltage compared to the positive supply voltage, you will end up with asymmetric transfer characteristics, asymmetric threshold voltages. Same I've shown here. The only difference here is that you will not have unique solutions in this case, like we did it in the previous examples, right? Previous examples in the last lecture, for asymmetric threshold voltages, there was a unique value of beta and Vref. Okay. Similarly, there was a unique value of beta 1 and beta 2, which was satisfying those conditions. Here you will not have that. Okay, because there are 3 unknowns and 2 equations, so you won't have that, but you can still get to close to the desired values. Okay, there will be some value of VSAT1 and some values of VSAT1 and VSAT2, VSAT1 and VSAT2, which will give you the desired threshold voltages. So finally, is there some other approach by which I can realize Schmidt triggers with asymmetric threshold voltages? The answer to that is yes. That the other approach directly follows from the definition of Schmidt triggers. So which is why I received a lot of comments when I was posting my initial lectures asking, this is just theory, right? When I was explaining how Schmidt trigger works, I saw some comments saying this is just theory, tell us practice. Remember, we are living in the age of artificial intelligence. Okay, in the age of artificial intelligence, I believe knowledge and even calculated application of knowledge, even blind application of knowledge is not going to be of much value. If you, let's say, you ask your LLMs to say, okay, I want a non-inverting Schmidt trigger designed to me with a certain low to high and high to low threshold voltages, it will do that job for you. Even right now, see, 5-10 years ago, we had to sit and write all these equations. Now probably even now itself we can do it. The softwares are not there yet, LLMs are not there yet, but very soon we will be reaching a stage where within a few years, where you give a certain architecture and tell, okay, I need this threshold voltages, give me all the design variables, what should be my resistor values and what should be the right op-amp architecture, op-amp IC that I should choose. And AI or most of the LLMs should be able to tell you all that. Okay, where I believe still humans will have an edge is in greater reasoning. Still LLMs cannot out-reason humans. Okay, LLMs make mistakes in complex reasoning tasks. I've heard mathematicians say that LLMs make a lot of mistakes when it comes to mathematical proofs. Okay, especially it's able to solve all very interesting Olympiad level mathematics questions, but if you ask an LLM to derive a proof doesn't have a unique solution. It requires some ingenuity, some better human reasoning and all that. It's still struggling in those parts. Okay, so I believe that's the struggle machines will face in the future, and that is where humans, you should have an edge over machines when you understand the theory, a deeper understanding of what's happening in the circuit. So if you recall, I'll come back to this discussion. If you guys recall, I said the whole idea behind Schmidt trigger is that the low to high and high to low threshold voltages should be different. Okay, It's true for both symmetric and asymmetric. In symmetric it will be negative of that, in asymmetric it need not be negative. Okay, it will be some other voltage. So the thing is that they both have to be different. So what should a Schmidt trigger do? If you can start with a simple comparator. You can start with a simple comparator. Okay, I'm showing here a non-inverting Schmidt trigger. So I need to have a certain threshold voltage. It can be, let's assume VLH is a threshold voltage. VLH will be the point where the output goes from low to high voltage. Okay, so as you keep increasing your input, your output right now is minus Vsat. Okay, it's negative, right? So because your input is not exceeded, I'm assuming the input is starting from a huge negative voltage, so I can assume output is also at minus Vsat. When the output is minus Vsat, you want the threshold voltage of the comparator to be VLH. So you can put an inverter to this and create a logic high voltage and control this switch. Okay, this switch will be a short if your output is minus Vsat. And now the threshold voltage, the comparator's threshold, the inverting the voltage at the inverting terminal of the comparator will be VLH. Now when your input exceeds VLH, your output will go to plus Vsat. The moment your output goes to plus Vsat, remember what I said? A Schmidt trigger is a circuit with memory. It should be immediately able to change its threshold voltage. It should have the capacity to change its threshold voltage. So immediately when the output goes to plus Vsat, this switch will be open. So which means it has disabled this threshold voltage. You should put another switch which will be turned on when your output is plus Vsat. Okay, when your output is plus Vsat, you want that switch to be on, and that threshold voltage will be VLH. So now if I am decreasing my output voltage plus from Vsat, the threshold voltage to the comparator will be at VHL. So this is what I mean. So depending on the output voltage, you want your threshold voltages also to change. I'm just applying the definition, the theory, what we discussed in the previous lecture. I'm just translating that theory into a circuit idea. That's it. All you need is just two switches that operate on, two different logic levels and the two threshold voltages. That's it. I've built my non-inverting Schmidt trigger. So when the output is plus Vsat, output is minus Vsat, VLH is being fed as a threshold voltage to the comparator. When the output is plus Vsat, this switch will be open, so VLH will be disabled, and VHL will be now connected to this op-amp's input. And now and the op-amp output will trip at a different high to low voltage. You can apply the same logic to a inverting Schmidt trigger as well. Inverting Schmidt trigger, I just have to flip the voltages. Okay. So for an inverting Schmidt trigger, I have applied the same logic. Assume that your input is a negative voltage, huge negative voltage, which means output is positive. If output is positive, we need to find out the voltage at which it goes to high to low. Okay, the point of interest is VHL. So if your input is positive, you want to turn on a switch and apply a threshold voltage of value VHL. Okay, when your input exceeds VHL, your output will go to minus Vsat. You have to then disable this switch, open the switch and enable another voltage. Okay, I've just used a not symbol here to just indicate that that switch will be closed when your output is negative. If your output is logic low, this switch will be closed. So if your output is logic low, in this case it's minus Vsat, this switch will close and the threshold voltage will be at VLH. Okay, so that's what if your output is minus Vsat, then as you keep decreasing your input, when your input voltage goes lower than VLH, your output will go to plus Vsat, and immediately your threshold voltage will also change. So this is what I mean, understanding the theory very well. See here, I just applied the theory which I discussed in the 3 lectures ago and just build the circuit based on that theory. Okay, I mean, you will see some circuit realizations using some switches, but conceptually this is what the circuits are doing. If you just probably In some papers, or if you Google, you may find some circuits which will resemble this architecture. Okay, but conceptually this is what it means. Immediately when your output changes, you want the threshold also to change. How do you do that? I just use switches and two different threshold voltages, and I've built my Schmidt trigger. In the circuits that we have been discussing so far, we just indirectly we are doing that. Okay, and yeah, for Schmidt trigger with symmetric threshold voltages, it was much simpler implementation. It gets a little bit slightly complicated with for asymmetric thresholds, and you can even come up with very interesting architectures, if you understood the theory very well. Okay, so that's my 2 cents on why theory is very important. Okay, so remember this, you don't have to even look for data sheets and find out, okay, how did those engineers design the circuits, because that's a knowledge available already documented by some engineers. So LLMs will be aware of that. So you just have to ask the questions. Okay, I want to design the circuit for this application. These are my 8 current limits and all that. Maybe see, what I've also noticed with LLMs is that LLMs are a much greater and a more powerful tool in the hands of the knowledgeable. Okay, if you are aware of things, it always helps. Okay, so which is why learn theory, why it works, why a certain thing is the way it is. These things will be greatly helpful in the age of LLMs and artificial intelligence. Okay, so I will keep posting. I do receive a lot of messages from students asking to post videos on this. I am occupied with some other very important work, so which is why I'm not able to find time. But yeah, do keep messaging me, do keep sending me if you have any circuit related doubts. Once in a while when I find time, I'll make videos on it. Okay, thank you.